Here's an example, a real-world example. And so we talked about component form. A term we didn't use last time was polar form, okay? So here's force vectors A and B at the origin. Find a component representation of each vector. So what is that? We know that component representation is, that's kind of like an ordered pair, but not an ordered pair really. And so this is our component form. And what did those components symbolize or represent? Yeah.
Horizontal and vertical movement.
Not necessarily movement. So if it were a displacement vector, yes, it would be like movement. Yeah.
Horizontal and vertical change.
Yeah. So like an x direction variation, right, and a y direction variation. So whatever quantity it is we're measuring with a vector. So those are variations in horizontal and vertical. And so that being the case, that means that vectors are mobile, right? So a vector, we can put its tail anywhere. This doesn't change, right? So how much variation represented in the x direction and in the y direction doesn't change based on where the vector is located, right? So vectors are mobile. Remember that. All right, so that's, but then the polar form goes back to what we said at the very beginning about vectors, that vectors have two aspects. What are the two aspects of vectors? Yeah.
Magnitude and direction.
Magnitude and direction. So polar form is kind of like the, goes back to the meaning of vectors. It's where you're given a magnitude and direction. So this diagram is giving us what? Is it giving us component form or polar form? Yeah, this is giving us polar form because it's giving us the magnitude of each force, and then it's giving us a direction by way of angle. So this angle is our standard trig angle, right? 40 degrees swept counterclockwise from the x-axis. And this is 10 degrees, like swept, like north of west or something like that. And we could, you could rewrite that as a standard trig angle. What would the standard trig angle be for that one? Again, swept counterclockwise from x. 170, right? So another way to express that vector b, instead of 10 degrees here, would be like 170 degrees as a standard trig angle. That'd be another way to express that. So we're given polar form, and we want to find the resultant force both in polar form and component form. So the resultant force here is a matter of what? Is a matter of doing what with these two forces, right? So I got a force pulling the origin this way, and force pulling the origin this way. So the result, the overall force at that point would be a matter of what? Doing what? You're just adding, right? We're just going to add those together. And so, is the magnitude going to be 6? No, because they're different directions, right? So how am I going to add these two vectors together? What's going to be a convenient way to do that? Or we talked about last time, adding, yeah.
Sine and cosine.
In order to find what? Yeah.
The component.
Yeah, so if we have A and B in component form, then we have apples to apples with our x variation and our y variation, and we can just, it'll be easy. So why don't you... So we're going to write A. And how am I going to write the x component of the A vector? So let's draw that, right? So the x component would be like this vector here, and the y component would be like this vector here. And so what mathematical tool is going to get us those two vectors? Or cosine and sine, right? This is going to be trig. So we're going to have 4 times cosine 40 and 4 sine 40. And then our b would be a couple different ways to do that. We could leverage the 10 degrees. We could use the 10 degrees. Or remember we said it was 170, so there's a couple different ways how we want to do this. So if we use the 10, what would we have for the x component? 2 cosine 10, is that right?
170.
What is our variation in x here? What do you see about that? Negative, right? If you're going to use 10, then you have to include the negative. If you used 170, cosine of 170 is already negative, right? Because cosine gives you the x coordinate. So if you did 170, you wouldn't have that negative. It would be part of the cosine. Make sense? Okay, and then we got 2 sine. So now, what's the resultant force? What's the resultant force? I mean, in general, like the structure of that. So if I want the resultant force, I will do what? We're going to add them, right? Resultant force is simply going to be A plus B. And now that we're in component form, adding is easy, right? Because you got apples and oranges, right? Changes in x can just add together, quantity-wise, value-wise. Changes in y can just add together. Okay, and so now pictorially, how do we add vectors? Remember what we do? If we want to do a plus b, what would that look like in an image? Tip to tail, right? So I'm going to take b and take its tail and put it on the tip of a. Like that. Same vector or different vector? Same vector, different location, right? Same vector, different location. And then what is represented? A plus b is represented by? Yeah, so it's like the cumulative effect of first A and then B would be starting at the tail of A and ending at the tip of B would be that would be like that. So applying those two forces is one for that point at the origin is one of the same as applying this A plus B force in this direction, right? So applying these two separately simultaneously is the same as just applying one force this way, and it's not going to be 6, right? It's going to be maybe something around 4 again, right? So something closer to 4. We're imagining the lengths, right? All right, so we can find, so what I'm going to start attendance. I want you to actually find the component, get some values here for a plus b, and then from that, see if you can come up with, so that would be component form. See if you can come up with on your own the polar form of a plus b. You have to think about how. I didn't tell you how to do that. You got to think about how you would do that. How would you get the polar form after getting the component form of a plus b? All right, so you can work on that. You can think to yourself, or you can grab someone to help you and do it together. Okay, let's get decimal approximation for a plus b. So let's do like maybe 3 decimal places. Samantha, did you get a plus b? Okay. Anyone get it? Values?
2.867.
Someone else get that? X component of the force 2.867. Different? Something different. What'd you get?
I got negative.
Not going to be negative. It's going to be in the first quadrant. Yes?
1.094.
1.094? Oh, there's some nods. I knew I'd get nods eventually. All right, 1.094. So maybe your calculator was on radians and not degrees, possibly. You gotta have these are degrees, so your calculator's gotta be in degrees. 1.094 and 2.910. 8. We have some consensus on those answers? Yes, I get some nods. Great. All right, so now let's just look at that and compare it to what we drew. It doesn't make sense. Does that look about right? What do we got? Like around 1 and around 3. So the y component is 3 times as much generally as the x component. Is that what this vector looks like? Yeah, so change of x of 1, change of y of about 3 times as much. So it looks like those numbers match up with the picture that we drew. That's all I'm getting at there. Okay? Now what about polar form? So polar form means we have to find 2 things. What's the first? Magnitude. How do we find the magnitude? Square root of the sum of the squares, right? And so we can write that as single bars or double bars is fine. We're going to do the sum of the squares, and let's do the square root. Remember last time we saw that comes from the Pythagorean theorem. What did we get for that value? 3.117. How about if I do 3? Yeah, sure. I'll come back. Oh, happy. All right. What's the units on that? Kilonewtons, right? Same as the originals. Good. And then what about the direction? How did you come up with the direction? Steven?
69.4 degrees.
And how did you get that?
I took the tangent of 2.918 over 1.09.
Close, not the tangent. Arctangent, right? Yeah, so yeah, you did it right. So it's the arctangent of, so we know that the tangent of the angle is the opposite over the hypotenuse, right? So that's y over x. So then to get that angle, you could do the arctangent of y over x, right? Or the variation in y. So we do the arctangent of the change in y over change in x. So that's a pre-calculus thing. And you got 69 degrees? 69.1? 4.1. So what about that? Does that look about right? The magnitude's 3, around 3, and the angle's about 70 degrees, according to our sketch. Yeah. So do little checks like that, right? Just like do little rough checks. You know, if you got like a negative for one of these and you drew this, something's wrong, right? Something's wrong. Or if you got something greater than 90 degrees, something would be wrong. Whether it's your sketch or your calculations, one of the two, not matching up. Questions on this example? So then that would be the polar form of the resultant force. Please.
Would we round using significant figures, or would you specify how many decimals you want it rounded to?
If I didn't specify, then use significant figures. How about that? But that's on my list. That's very low priority. So in terms of, I'm like, I want you to understand things. If you don't have the right number of decimal places, that's very inconsequential to me. Yeah. So I'm much more interested in you understanding principles than splitting hairs on decimal values. Now web work, put in expressions, and you don't have to worry about that, right? Yes, you're gonna have to get answers on web work. You want to get it right. Put in expressions, and you don't ever have to worry about how many decimal places. Other questions? Okay, so let's talk about R3. Let's do some stuff in R3 here. Oh, actually, I got a little bit more of this here. So I mentioned scalar multiplication last time, but let's dive into that a little bit further. So there's actually 3 kinds of multiplication of vectors. This is the first and the simplest, scalar multiplication. And so it's when you multiply a scalar times a vector. And we talked about last time, what's the effect of that? What does that do? What's that? Changes the magnitude. So why do we call it a scalar? Because it's scaling the magnitude, right? The scalar scales the magnitude by whatever that multiple is. And then what about, so we haven't talked about direction yet. What about direction when you do scalar multiplication? Yeah.
If it's negative, it flips the direction.
Right. And if it's positive?
It stays the same.
Yeah, so a positive scalar will keep the exact same direction and scale the magnitude. A negative scalar will scale it, but then have it point in the exact opposite direction. Okay? So for the previous force example, we had 3A. What would 3A represent relative to the force A? Direction? Same. Magnitude of the force? 3 times as much. What about negative 1/2 b? Direction? Opposite direction. Magnitude? Half as much, right? So this is the idea of scalar multiplication. All right, so we already did that. We already answered that question. All right, so a unit vector is a vector with magnitude 1. We've already seen some unit vectors. What are they?
1, 0,
Right, 1, 0, and 0, 1 are very special unit vectors. Those are called the standard basis normal vectors. And those are I and j. So I and j are examples of unit vectors. Those are just very special unit vectors. But you can have unit vectors you can have a unit vector pointing in any direction, right? It'd be like the unit circle, right? Like any angle. If you thought about the vectors pointing from the origin to the unit circle, that'd be like all the possible unit vectors, right? All right, so remember this was our standard basis form of the vector, and then in component form, that would be what? 3, negative 5. And you should know how those things on the left and right side are mathematically equivalent, not just two different labels for the same thing. This is a mathematical statement. That is mathematically the same as that, and you should be able to prove that, like we did last time. Yeah, question?
How would you make the opposite direction? Would you just throw negative in front of each number? Or?
Yeah, so if this vector is saying like a variation of 3 in the x and a variation of negative 5 in the y, then in the opposite vector, what would the variation in x be? Negative, and the variation y would be? Right, so yes, changing the direction would be like scalar multiplication by negative 1. Just change the direction, and so that it gives you the opposite of both components. Yep. Other questions? Okay, now I want to find a unit vector in this direction. So does this have a magnitude of 1? Greater or less? Greater, obviously, square root of 9, square root of 34, right? So the magnitude of this is square root of 34. So if I want the unit vector in this direction, then I need to scale this vector. If I scaled this vector, I would maintain the direction. So the question is, what do I scale it by? What do I scale this vector by so that it's in the same direction? So it'll be in the same direction, but I want its resulting magnitude to be 1. Yes, sir?
What of the magnitude?
Yeah, so I want it, so if I take 1 radical 34th of it, right, if it has magnitude of radical 34, then I want 1 radical 34th of it, and that'll give me magnitude 1. Should make sense. Does it make sense? So I'm going to take 1 over radical 34 of 3 negative 5. So 3 over radical 34. Negative 5 over radical 34 will be what? That'll be a unit vector in the direction of my original vector. So it has magnitude 1, because it's a unit vector now. Make sense? Okay, so then kind of taking that a step further. So now I want a vector with magnitude 8. In the end, I want my vector to have magnitude 8, and I want it to be in the opposite direction of 3, negative 5. So here's the key to these kinds of questions, and this is an important question that you'll come across a lot. The key to this is think of doing it in 2 steps. That's your hint. What 2 steps could I do to get there rather than I do it all at once, right? So the hint always for this is two-step process. So actually, let's change it up since we already did. So I'm going to change this to how about negative 2i minus 10j. So now I want a vector with magnitude 8 in the opposite direction of negative 2i, negative 10j. Go. What would that be getting you?
It would be like 1 over root 104.
Right, and what would that be getting for you? So you're going to start by doing 1 over
even actually do like decimal approximation.
That's fine. My question is, what is that?
Oh, it makes it 1. Like it makes the vector magnitude 1.
Right. Yeah. So if I want a vector with magnitude 8 in a certain direction, start by finding the unit vector. That's kind of the key here. Start by finding the unit vector, and this is that, right? This is the unit vector in the direction there. And now if I want it to have magnitude 8 in the opposite direction, that's the easy part. So the hard part is just remembering to start with the unit vector. That's the hard part, is remembering what to do. And that would be start by finding the unit vector. Once you have the unit vector, it's like, oh, now this is easy. I want magnitude 8. What do I do? If I want the opposite direction, negative 8. So I'm going to do negative 8 times that thing. So altogether you get 16 over radical 104 and 80 over radical 104. Doesn't make sense. So this is basically, given any vector, you could find a vector with any magnitude in the same direction or in the opposite direction. That's what we're talking about. Given any vector, can you find a vector in the same direction or the opposite direction with any magnitude? That's exactly what this problem is about. Any questions on that? All right, let's jump into R3. So, so I said before, it wouldn't be wrong to say that this is a course in vector calculus. Another way you could frame this is a course in three-dimensional calculus. Three-dimensional calculus. All your life, all of your math life to this point, most of you have lived here, right? What is this? The Cartesian plane, the Cartesian or the rectangular coordinates. This is where we've lived. So now we're going to start, and that's all the way through Calc 2, right? Through Calc 2, we did everything in two-dimensional Cartesian plane or rectangular coordinates. Well, no, actually, rectangular coordinates is more broad than that. The plane, right? So this is the two-dimensional plane. So Calc 3 is all about taking all that we've learned in calculus before and applying it to 3 dimensions. Okay? So I want to call that, this is called R2. Why is it called R2? Reals. The reals in the x direction and the reals in the y direction give you a plane. So this is R2, 2 dimensions, right? R2. And so 3-dimensional space would be R3. So now we have the reals in the x direction, the reals in the y direction, and the reals in the z direction. And so in order to, we have to trick our eyes to draw that in a plane, right? So this is a planar rendering of 3-dimensional space, right? And so you might expect that, if you didn't know any better, you would think this axis is what? X, and this was Y, and then our new one coming out, so just you have to, your eye should see this as coming straight out of the board. You see that? Or the screen. So this is supposed to be depicting this coming straight out at you, okay? But that's not how they're labeled. What we've got is, this is what we do. So I'm going to take, so imagine here's the XY plane like this. So I'm going to grab the XY plane with my hands like this, ready? And I'm going to turn it this way, and then I'm going to set it down this way. So try it again. So here's the XY plane, the board. I'm going to pull it off like this. So I got X and Y like this, right? I'm going to fold it down like this. So where's the X-axis? That's the one coming straight out at you. Where's the Y-axis? To the right. Up and down now is the Z-axis. And we'll see when we get to functions in 3-dimensional space, we'll see why this is the case. Okay. Okay, so those are axes. Again, you've got it in your brain. You're thinking that x-axis again is like this. coming straight out. So y and z are in the plane of the screen, okay? Y is horizontally in the screen, z is vertically in the screen, but x comes straight out at you like this, okay? So then when we plot ordered pairs, so say, so now that's ordered triples. So, graphing in R3 is just always about points, either a point or a set of points. So the point, say, 4, 2, 3. Where do we go first? So positive x direction is coming out at you. 1, 2, 3, 4. And then, let me do a different pattern here. How about 3, 4, 2? Sorry. It's going to be easier to draw. So 3, 4, 2. Come out 3. Then from there over 4 to the right. 1, 2, 3, 4. So now when you're drawing, you don't want it so the y equals 4 isn't straight up and down, right? Y equals 4 is going to be parallel to the x-axis. So you can imagine that. Y equals 4 is going to be along the line that's parallel to the x-axis. So going over 4 from x equals 3 puts you here, and then from there, up 2. Now notice, that's not at this level, right? Because we're out in front. So there's a 3D. If you can draw the box, that's very helpful. So what did I say? 3, 4, 2? So let's set it at 3, 4, 2, and I'll turn on the point. So that looks like it's on the y-axis, but it is not. So I'll show you how it's not. If you draw the box, now you can see that it's I'm having a tough time here grabbing this and turning it. Okay, that's a little better. I still haven't learned how to do this. Control it. There we go. Yeah, struggling. Almost there. There we go. All right. That's good. So if you can draw, and all your edges of your box will be parallel to one of the axes if you draw it correctly, and that will help you, okay? So that's the point. That red point there is the point 3, 4, 2. Okay, so how far is that point from the YZ plane? So the YZ plane, remember that's the plane of the screen. So how far is it from the YZ plane? 3, right? So it's the x-coordinate. The x-coordinate will give you how far it is to the YZ plane, which is this plane here. Okay, how far is it to the x-axis? How far is, or z-axis? How far is that point to the z-axis? Okay, so that would be the distance from here to here. See that? That distance right there is how far that point is to the z-axis. So what was this? That was our 3. This is 4. So from that point to the z-axis is 5. So it ends up being a 3, 4, 5 triangle. So that diagonal distance there is to the point 0, 0, 2, right? So that would be, if I ask you for the distance from that point to the z-axis, I'm asking you, how far is it from 0, 0, 2? Make sense? Okay, so let's talk about vectors. So vectors in space, all the mechanics, all the mathematics we've dealt with so far are the same. It's just you have a third component. And what will that third component be? Z? What about Z? It's not a Z coordinate. What will that third component represent? The variation in Z, right? So I have variation in X, variation in Y, variation in Z. So let's find, can you find, if this point and the midpoint here right there is P, the midpoint of that side of the box, and that's the point Q, can you find the vector QP? What would the vector QP be? So P is on the midpoint of that lower edge of the box. Q is that corner of the box, and I want the vector QP, which means its tail is at Q, and its tip is at P. This vector right here is QP. So how would I do that? So first of all, what are the coordinates of P? 1.5, 4, and 0. Make sense? That's on this edge down here. And what's the coordinates of Q? So it has an x coordinate of 3. Y coordinate is 0. It stays there. And then up to. If I lose you, ask, right? So lots of you are saying it, but then lots of you are quiet. So QP will be the vector with tail at Q, tip at P, and it will be X component is negative 1.5, right? 4 and negative 2. Or final minus initial, right? Final coordinate minus initial coordinate will get you the amount of change in each one. Okay, so how would we find the magnitude of that? The magnitude of QP would be? Yeah, so it's the same thing. We just got another component to deal with. So the square root of. Now, where did those three numbers come from? Let's generalize this. So whatever that turns out to be, I don't really care about the final answer, but what if we were to generalize that? Let's say that Q was x1, y1, z1, and P was x2, y2, z2. Then, in general, where is that magnitude of QP coming from? Square root of what? Yeah, so that thing that we're squaring is what, like the variation in x, and that comes from x2 minus x1. Does everyone see that? So we do x2 minus x1 squared plus, I'm sorry, this is magnitude. Should have the bars around it. It's not the vector. Now it's just the magnitude of it, right? The vector has the components. Right? Now, we just found something that's also apart from the fact that QP is a vector, right? What did we also find, regardless of this vector QP? What's that? Yeah, so we just found the distance from point Q to P, whether you have a vector there or not, right? So this is a generic distance formula for R3. From x1, y1, z1 to x2, y2, z2, that's the distance. Okay, so now suppose from this point, I want to mathematically show all points a distance of 2 from, let's call this point, say, R. No, I don't want to call it R. I'm going to call it something like B. So I want to mathematically represent all points that have a distance of 2 from point B. I want to use the distance formula to do that. What's the coordinates of point B? He said 3, 4, 0. Agree with that? So if all points that have a distance, so all points could be represented how? All points. How could I represent that?
2 squared equals.
But just the part of this all points will be represented by, yeah, so I need variables, right? So by all points, I'm going to say x, y, z, and on all points x, y, z that are a distance of 2 away from point B. How could I apply the distance formula to write out what that would be? 2 equals square root of x minus 3, good, squared,
plus y minus 4 squared plus z minus 4 squared.
So that equation would represent all points in space, x, y, and z, that are distance 2 away from 3, 4, 0. Does that make sense? And do you all have a vision of what that is? What is that?
Sphere.
That's a sphere. So if I come up here and put, I know we're a little bit older. Thank you for your patience. Just want to finish this. Okay, so, and I want to square both sides. If I square both sides, I get x minus 3 squared plus y minus 4 squared plus z squared equals 2 squared. Yeah, let's write it as 2 squared. What is 2 for the sphere? The radius, right? So it looks like an egg. I'm having a lot of trouble rotating this. There we go. Why does it look like an egg? My scale must be off. Yeah, so I've got a smush scale in one direction or another. So it looks kind of like an egg. But so basically that's our equation of a sphere then. A sphere is based on the distance formula. And what is 3, 4, 0? Center, right? 3, 4, 0 is the center. And the radius is 2. So just pretend that's the sphere. It's the axes are stretched in my rendering, so it's squishing and but it is a sphere.